Good day, viewers, and welcome to Jalo Science Academy, your best hub for learning sciences. Of course, this is part 3 of our chemical combination video. And in this video, we'll be looking at ionic character in covalent bonds. Ionic character in covalent bonds is determined by the electronegativity of the reacting species, the species that are in a bond. And electronegativity, we know, is the ability of a species to pull bonded pairs of electrons or electrons in a shared pair towards itself in a covalent bond. And the electronegativity of the species determines whether the bond is going to be a polar covalent bond or if it is going to be a non-polar covalent bond. So we start off with polar covalent bonds, which give rise to polar molecules. Now, polar molecules are formed as a result of the electronegativity difference that exists between the species reacting to form a bond. So as a result of the electronegativity difference that exists between the species that are forming the bond will lead to a displacement of the electrons towards the most electronegative species in that bond. If it is between two electronegative species, okay, or when the electronegativity difference is large. So the electron cloud in the shared pair is going to be displaced towards the most electronegative species and thereby brings about a separation in charges. It brings about a separation in the charges, thereby causing the electronegative species to get a former negative charge we call a delta minus, and the least electronegative species getting a formal charge we call delta plus. So it brings about the separation of these charges. So let's look at examples. And you should also know that the degree of polarity depends upon the electronegativity differences between the constituent atoms or the constituent elements. If the electronegativity difference is vast, then that makes the molecules becomes more polar. If the electronegativity difference is small, then that makes them become less polar. So the degree of polarity depends on the electronegativity difference. First example we are going to look at is hydrogen chloride. In HCl, you know that hydrogen contributes 1 electron. So this hydrogen here contributes 1 electron to form a bond with this chlorine, a shared pair. Okay? So in this situation, what happens? The electronegativity difference between chlorine and that of hydrogen is great. Chlorine is more electronegative than hydrogen. And in that regard, what happened? This electron here is going to be displaced towards the chlorine. And you have the resulting species to be this. So you see here the electron cloud is shifted towards the chlorine. And when this situation arises, what happens? This hydrogen, the electron cloud, have shifted away, so it's going to get a formal charge of delta plus, because the electron which makes it electrically neutral have moved off. It is only the proton that remains, so it gets a positive charge, and here an electron has been added, which brings about the number of electrons outweighing the number of protons. So this gets a formal and negative charge. This is delta plus and this is delta minus. So we can therefore say hydrogen chloride is a polar molecule. Another example we can look at is aqueous ammonia. In the ammonia molecules, the electrons of the hydrogen are closer to the nitrogen atom. Reason being, the nitrogen is more electronegative. So when the bond is formed, this is actually what happens. Nitrogen has a lone pair here with 3 unpaired electrons, it and hydrogen bonding, forming a bond here. So being that this nitrogen is electronegative, this electron here is going to be tilted towards the nitrogen atom, and the electrons here also tilted towards nitrogen atom, and the other electrons in this bond here tilted towards the nitrogen atom, thereby producing this. You have the nitrogen here at the center, and then you have the electron cloud coming around the nitrogen, and you have the hydrogens here staying far off. Okay, so for this reason, the nitrogen is going to get a delta minus charge because the electrons are being displaced towards the nitrogen, because the nitrogen is electronegative than the hydrogen. So the hydrogen here gets a positive charge, delta plus, delta plus, delta plus. Mind you, this is the lowercase letter for delta, okay? It is a small letter. So it gets these charges. So that also tells us that ammonia is a polar molecule because the nitrogen atom in it has the ability of pulling the shared pairs of electrons towards itself. So the electron cloud is shifted towards the nitrogen atom. Another example of this is water molecule. Now, water has this shape. So this is the water molecule, how it looks like. So in this situation, what happens here? This electron that is closer to the hydrogen here in this bond, and this other electron closer to the hydrogen here in this bond, are going to be shifted towards oxygen because oxygen is more electronegative than hydrogen. So you discover this. You will discover that the electron cloud is being shifted towards the oxygen. So the oxygen is going to get a delta negative, the hydrogen a delta positive, and this other hydrogen a delta positive. So that also tells you that water is a polar substance. It is for this reason that water, despite being covalent, it is able to dissolve ionic substances or ionic compounds. So next up, we look at non-polar molecule. Non-polar molecules can be formed in 2 different ways. One is if they are formed between the same atoms. Example, if it is formed between a hydrogen and a hydrogen, each hydrogen contributes 1 electron here. So what happens? In this situation, the electron pairs contributed are going to lie exactly midway. Okay, it lies in the middle. This is going to be midway the species. It lies midway the species, meaning it will not be tilted to any of the atoms because their electronegativities are the same. So in this situation, we say the center of positive charge and the center of negative charge are going to coincide. And this is where they coincide. This is where they coincide. Okay. So coinciding at this point brings about the electron being placed midway. And when the electron is placed midway, that brings about the species being electrically symmetrical. So the species becomes electrically symmetrical in this position. Thereby, no charge is being formed. So you get no charge here, no charge here, because none of the electrons are moving. So this is one way the species can be formed between atoms of the same element. For example, between hydrogen and hydrogen, or you can have it between oxygen and oxygen in the formation of oxygen molecule, especially when we look at species that are diatomic. Okay, for example, formation of chlorine, and the formation of nitrogen, etc., etc. So this is one way through which non-polar molecules can be formed because there is no separation of charge here. The center of positive and negative coincides at the center. So we look at the second situation. So the second example is a situation wherein you have a covalent bond being formed between two different atoms wherein their electronegativity difference is so small. So this is a situation of different atoms. Now, between different atoms, when their electronegativities are so small, that brings about what? The charges being cancelled out, okay? The charges are going to be cancelled out. If you have them in the form of vectors, they'll be cancelled out. A typical example we can look at one is in methane, okay? CH4, the first member of the alkanes. So methane here, though what I'm going to draw is not the correct shape. If we look at methane this way, carbon is slightly electronegative than hydrogen when you look at it. So here, the electron cloud is supposed to be pulled towards carbon. So we indicate a vector pointing towards carbon, from hydrogen also pointing towards carbon, from hydrogen pointing towards carbon. Now these vectors are opposite. What happens? The vectors are going to cancel out. These ones opposite, these vectors will also cancel out, thereby resulting in no charge. So that makes the methane molecule non-polar. Another example we can also look at is the carbon dioxide molecule, CO2. Carbon dioxide, or we call it carbon dioxide in CO2. In CO2, you have carbon as the center being doubly bonded to two atoms of oxygen. Oxygen we know is electronegative than carbon. So what happens? You have the electron cloud is going to be pulled towards the carbon. This one also being pulled towards the, is going to be pulled towards the oxygen rather, and this one also pulled towards the oxygen. So what happens in this situation? These vectors are moving in opposite direction, so they can cancel out, thereby causing the carbon dioxide to also be a non-polar molecule. Okay, so these are examples of non-polar molecules. It can be between the same atoms, wherein you have the charges coinciding at the center and making the electrons line exactly halfway middle, especially when we deal with diatomic molecules like the hydrogen gas, the oxygen gas, in the chlorine molecule, in the nitrogen molecule, etc., etc. As far as you have the species that are reacting are atoms of the same elements. So next up, we are going to look at dipole moments. For dipole moments, we talk of molecules that are having two equal and opposite charges that are separated by a certain distance are said to possess an electric dipole. So meaning if you have molecules that are having two equal and opposite charges and they are separated by a certain distance, those molecules said to possess what we refer to as an electric dipole. Let's say, for example, you have here a particular species H and another one A. These molecules here have two opposite and equal charges. So these molecules are said to get what we refer to as an electric dipole. So this is a pole here, which can be positive, a pole here, which can be negative. So this makes them to be dipole. This is called an electric dipole. In these molecules, the center of negative charge and the center of positive charge does not coincide. So the extent of polarity in such covalent molecules is what we refer to as a dipole moment, because you have their negative charge and their positive charge does not coincide. So we call it dipole moment. From the word di, it means two. So there are two poles. So dipole moment is the product of the magnitude of the charges and the distance separating them. So talking of the product of the magnitude of the charges, meaning the size of the charges, and the distance separating them. And it is denoted by the Greek letter mu. So this is what we denote dipole moment with. So this is the product of the magnitude of the charge and the distance separating them. This is what we refer to as a dipole moment. Next, we are going to look at the importance of dipole. How important is dipole moment? So the importance also means the uses. One use of dipole moment, it helps us to measure the shapes of molecules. And dipole moment also helps us to determine the degree of polarity in diatomic molecules. And dipole moment also helps us to predict the nature of the bond that is formed, depending on the electronegativity of the species. And then we'll know that the bond will be more polar if the electronegativity difference between them is very high. So if you have high electronegativity difference, that tells you the bond formed is going to be more polar. But if the electronegativity difference is small, then the bond formed will be less polar. And also, the greater the electronegativity difference in the bond, the more ionic the bond becomes. So it becomes more ionic. That is, the more polar it is. The more electronegativity difference, the more ionic the bond becomes. If the electronegativity difference is high, the bond becomes more ionic. And if you have the electronegativity difference to be 1.7, then we can say the bond is 50% covalent and 50% polar, meaning half covalent and half polar. If you have it to be around 1.7, okay? And if the electronegativity difference is more than 1.7, then the bond becomes more ionic and less polar. So as the electronegativity difference increases, that's how the ionic character of the bond also increases. So you have to note that. So let's say, for example, if a bond can be formed between a highly electronegative species with an electronegativity value of around 3.8, with a species whose electronegativity values around 1.9. So if you look at these differences, you will find out that you also get an electronegativity difference of 1.9, and this is 1.7. So this bond that will be formed becomes more ionic. Okay. So next we can differentiate between polar covalent and non-polar covalent. Now, in polar covalent here, you have what? The electron cloud shifted towards the electronegative atom. So the electronegative atom pulls the electron towards itself. Whereas in non-polar covalent, the shared pair of electrons is evenly distributed. So there is an even distribution. Even distribution, okay, of the shared electrons. So there is an even distribution of the shared electrons. Two, in polar covalent here, we have what? Separation of charges taking place. There is separation of charges. So the charges separate. In non-polar, no separation of charges. Separation of charges, because the center of positive charge and the center of negative charge coincides. And in that coincidence, that brings about no separation of the charges. Three, in polar molecules, the bonds are not symmetrical, non-symmetrical molecules. So non-symmetrical molecules are formed, whereas in polar molecules, the molecules are symmetrical. So the molecules formed are symmetrical, okay? Because you have the electrons being evenly distributed. In this case, there is no even distribution. So that brings about this one being asymmetrical, whereas these ones are symmetrical, okay? So these are the differences between polar covalent and non-polar covalent. So next up, we look at the properties of covalent compounds. For properties of covalent compounds, one, these compounds exist purely as molecules and not as ions. Two, covalent compounds are poor conductors of electricity because they are molecules and they don't form ions. Three, they have a low melting and boiling point. Four, covalent compounds are generally insoluble in polar substances. So they are generally insoluble okay, they only dissolve in non-polar substances. So they only dissolve in non-polar substances. An example like benzene, like carbon tetrachloride, like ether, like toluene, like phenol. Okay, so those are substances in which they dissolve, but generally they are insoluble in polar substances. For example, like in water, that is a polar substance. You have the covalent compounds being insoluble in water. So next up, we look at metallic bonding. Metallic bonding is a bond between atoms within a metal. So if you have atoms within a metal, being bonded to each other, we refer to it as a metallic bonding. It involves the attraction between the cations and a sea of delocalized, or we say mobile electrons. So it is the attraction between cations and the sea of delocalized or mobile electrons. The high melting and boiling point of metals is as a result of the strong electrostatic force of attraction between the cations here and the sea of delocalized electrons. So the strong electrostatic force of attraction that binds these together give rise to metals having high melting and boiling points. So it's as a result of the attraction between the cations and the sea of delocalized electrons here. So we say the simultaneous attraction between the electrons and the positive kernels of the metal holds these atoms together, makes the boiling point and melting point very high, and makes them to be much more stronger. And also the valency electrons in metallic bonds are not localized. If we say something is localized, meaning it is stuck in one position, but these ones are delocalized, meaning they can move about freely. And that is also what leads to metals being good conductors of electricity, as electricity is a flow of electrons. Because the electrons are flowing in there, they are mobile, they can leave one field of influence and enter another field of influence. So because the electrons are mobile and then they can leave one field of influence and go to another field if there is a stress, that brings about also the malleability and ductility of metals. So metals are malleable and ductile as a result of the delocalized electrons that are there. And that also means the bond in metals are non-directional. It's a non-directional bond, okay? Because it can bond with any atom around it. And then also that makes the metallic bonds a bit weaker than the covalent bonds. It makes them weaker than the covalent bonds because the bonds are non-directional. Next, we look at the electron C model. A metallic crystal consists of large number of atoms. That's a metallic crystal. So a metallic crystal consists of large number of atoms arranged in a regular pattern. We can think of this like the positively charged cations, or referred to it as the kernel, being immersed in a sea of electrons, wherein the electrons are free to move about, okay, within the boundaries of the crystal. Let's look at it this way. Let's say this is the crystal. Yeah, so in this crystal, you have the cations, okay, that are being immersed. The cations, also call them the kernels, that are being immersed in a sea of delocalized electrons, wherein the electrons are free to move about these lattice, this crystal here. So they move about this lattice, they don't go out. Now, if only you have cations like this all over the place, if only you have cations like this all over the place, there is going to be an electrostatic repulsive force that will burst the lattice asunder. So the electrostatic repulsive force will burst this lattice asunder. But now what acts as a cushion and what acts as a glue which holds these positive kernels together? These plus signs are the cations, or you call them the kernels. And then around this, you have negative charges. There are negative charges. So these guys here are the positive kernels, okay? And then these ones you have are the sea of electrons. So these are the ones that holds these ions together. They prevent them from the electrostatic repulsive force. So these electrons here serves as glue. It serves as glue holding them in position. And at the same time, the electrons can leave one field of influence and enter another field of influence, meaning they are not localized, they are delocalized. They are mobile. They move about the lattice. Okay, so we can represent it in a more nice way like this. This here, the negative charge represents the electrons. Okay, so we can represent it like this, that you have a positive charge here, you have an electron here, positive charge here, an electron, positive. So it is better represented like this. So this is how they are held. Okay, and this electron, one electron, can leave this field of influence and enter this field of influence. This one can leave this field of influence and enter this field. This one can leave this and enter here. So they are mobile, they can move about the lattice. As far as they're inside this lattice, they move about it. So the electrostatic force which binds these cations and these electrons is what we refer to as a metallic bond. Okay, so the electrostatic force binding the delocalized electrons, mobile electrons, and the positive kernel here, or the cations, that is what we refer to as the metallic bond. And the stronger the force, the stronger the metallic bond. The weaker the force binding them, the weaker the metallic bond. Next, we have to look at the factors that favors metallic bond. Metallic bond is favored based on two factors. One, we deal with the number of valency electrons, and two, we deal with the size of the atom. Okay, so these are the two factors that favors the formation of metallic bonding: the number of valency electrons used and the size of the atoms. So we look at the number of electrons used. So we look at one. number of electrons used. The greater the number of electrons used, the stronger the metallic bonds. So a bond wherein more electrons are used in the formation of that bond, then that bond is going to be much more stronger. Let's compare the number of valence electrons used. For example, the alkalis in group 1 compared to the alkaline earth metals. The alkali, let's look at sodium, and then we look at magnesium. Now, sodium uses only one bond, that is the electron in the 3s orbital, 3s1. So sodium uses only one electron in forming the metallic bond, whereas in magnesium, magnesium uses the electron in the 3s, that's a 3s2. So both of them are using the electrons in their 3s orbital, but sodium is using only one electron, whereas magnesium is using 2 electrons. So in that regard, the metallic bond in magnesium is going to be much more stronger than the metallic bond in sodium. And similarly, in that vein, the metallic bond in Al, the aluminum, is going to be stronger than in magnesium and than in sodium, because Al uses the 3s2 and the 3p1. So in total, aluminum uses 3 electrons in forming a bond. So the metallic bond in Al is going to be much more stronger than in magnesium, and the one in magnesium is going to be much more stronger than the one in sodium. Aluminum will have the strongest metallic bond of the 3. Next, we look at the size of the atom. Size of the atom. Now, for the size of the atom, the smaller the atomic size, that tells you the greater the force of attraction between the positive center and the electron cloud. And that brings about the stronger the metallic bonding. So atoms with smaller atomic size gets a stronger metallic bond. So smaller atomic size is equal to stronger metallic bond. So the smaller the atomic size, the stronger the bond. Let's look at group 1 again. We try to compare between sodium and potassium. Sodium here uses the 3s1 electron, and you come to potassium. Potassium uses the 4s1. So both of them are using an electron each. But you look at the configuration of sodium is 2, 8, 1. Potassium is 2, 8, 8, 1. So meaning the atomic size of potassium is bigger than the atomic size of sodium. In that regard, the metallic bonds in sodium becomes much more stronger than the metallic bond in potassium, because sodium has a smaller atomic size when compared to potassium. So the metallic bond in sodium is much more stronger. If you compare between sodium also and lithium, sodium uses the 3s1 and lithium uses the 2s1. So sodium has 2, 8, 1 configuration, and lithium has just 2, 1 configuration. So the atomic size of lithium is smaller than the atomic size of sodium. In that regard, lithium has a stronger metallic bonding than sodium because its atomic radius is smaller. So that tells you smaller atomic radius favors stronger metallic bonds. So meaning metallic bonds decreases down the group, because as we move down the group in the periodic table, the atomic radius increases, and metallic bond increases across the period. As we move across the period, the atomic size will decrease as a result of what? The nuclear charges increasing. So they experience a stronger pull towards the nucleus. So it is number of electrons used. The more the number of electrons used, the stronger the metallic bond, the size of the atom. The smaller the atom, the stronger the metallic bond. And the larger the atom, the weaker the metallic bond. And also stronger metallic bonds contribute to boiling point. They contribute to densities. So metals that are having stronger metallic bonds are high in density, and they also have high melting and boiling points. For example, magnesium has a higher boiling point when compared to sodium. It has a higher boiling point when compared to sodium. Aluminum has a higher boiling point when compared to magnesium. So the stronger the metal, the more dense it becomes, the more hard it becomes, and the higher the boiling points. So next, let's look at metallic bonding in the transition metals, the D block elements. Of course, we'll just focus from scandium to zinc. Now, the transition metals, when compared to these other metals, the transition metals are much more denser, much more harder, and having higher boiling points than these metals. Why does that happen? Because the transition metals involve their d orbitals. The transition metals involve the 3d orbitals and the 4s orbitals in the formation of the bond. Okay, and the more the number of electrons involved, the stronger the bonds. And then lastly, for metallic bonding, we look at metallic bonds in molten metals. Of course, we have metals that are molten, like mercury is a molten metal. In molten metals, the metallic bonds still exist, even though the ordered structure have been broken down, because you have them in molten state. And that is the reason melting point does not account a lot for bond strength. Rather, we look at boiling point, because the bond is loosened when the metal melts or when a substance melts, and the bond is completely broken down if it boils. So in molten metals, it is only the ordered structure that is being broken down, but the bonds are still there. Not until it boils, that is when the bonds are completely broken down. Of course, this is it for our bonding, metallic bonding to be precise. So thanks for watching our videos. You can like our video, subscribe to the channel if you are new, hit the notification bell to be notified each time we release a new video. You can follow us on Facebook. There's a Facebook page, Jalo Science Academy. You can like the page to be receiving our videos. You can also join our study group on Telegram, Jalo Science Academy, where you can drop your questions, your assignments, and we'll help you to solving your questions and assignments. Once again, thank you. Stay glued to this channel. Continue to share our videos, share our links, so that your colleagues too can benefit.